Yeah. First of all, I would like to thank the organizers for inviting me to this fantastic conference, a marvelous place, and to Peter for this introduction. He made me embarrassed. So let me start with the main point of the conference. Uh, I have to tell you that I knew Fiorini's name from my childhood. The Hungarian word for the name of the Hungarian currency is forint, and it comes from the Italian word Fiorini. And on top of it, my wife's family name is Virag, which is also Fiorini in Hungarian. So I was surrounded by Fiorinis. I checked the most important papers of uh, Stanley Fiorini with the highest citations, number of citations, and I found one surprising here. It's demographic growth, and it's the same person. So he is a very well known historian in Malta. So he has two important areas here. So let me show you a theorem dedicated to him. This is the statement, and so every lecture must contain a proof. So this will be proved here. I hope I was clear in the proof. So let me be more serious now. So everybody defined what intersecting family is, but I had to start with this. So when this is excluded, then we say that this is an intersecting family. And the celebrated result of Erdos-Ko-Rado is that if you have k-element sets, and their size is less than half of the underlying set, then you cannot do better than take all k-element sets containing a fixed point, and then you get this number. And let me show you a picture about one of the authors of this paper. I don't know if you can see it really. So this is Paul Erdos sitting after dinner in my house. He wanted to make a phone call and started to think about the number, what he wanted to dial. And he was so serious that he fell asleep. So this is a sleeping Erdos. There were so many words about this cycle method. I thought there are many graph theorists who are not familiar with extremal set theory. So I briefly show this cycle proof for the Erdos-Ko-Rado. So when I have such a picture, it's usually the elements are here. Now the elements are arranged along a cycle in some permutation. So x1, x2, x3, xn is a permutation of the first n integers. And so now we solve the problem for intervals instead of arbitrary subsets, intervals along this permutation. And of course, they are intersecting. So we solve an easier analogous problem to the Erdos-Ko-Rado problem. largest number of intersecting intervals of length k, and of this form. And you can see that it's very easy to feel, and it's maybe easier to prove that the best is when you fix some point and you take all the intervals containing this point. So, and this will be, the number of such intervals is k. So, of course, this is true, again, only when k is less than ½ And after knowing this, we can use an easy double counting. We count the number of pairs, such pairs where C is a cyclic permutation. Actually, I was always unsure if it's cyclic or cyclic, and I asked Imre Lieder and Richard Bruhl, sitting next to each other, what is the correct pronunciation, and one said cyclic, the other one said cyclic, so you can choose. And so we have the family, and we take these such pairs, but this is a cyclic permutation. F is in the family, and it's an interval along the cyclic permutation. So the two ways of counting is, first we fix F, the member of the family, and then how many such pairs we can have. Of course, we can choose first the member this many times, and for every fixed F, it's easy to see that this is the number of cyclic permutations where F, this given F, is an interval. And the other way, when we fix the cyclic permutation, then this is the number of cyclic permutations, and for every cyclic permutation, we can have not more than k because of the lemma. And this is the proof. So this so-called cycle method, so it was a small idea, and so, but it became a method because of many people, and I am very thankful to those people who made a method out of this small idea. First of all, Peter Borg, who had made an important contribution, and he's a host, of course, so he has to be the first one. But I tried to list all the people who are present or in our seminars in Hungary. So these people all use this method and developed with some new steps. So now I start to speak about some some generalizations. Two-part families. So we divide the underlying set into two parts, and one element and two elements, and so that was the wrong picture. It's not the right place. So on the left-hand side, we had R element, and the right-hand side, S element. So we consider those families which consist of such members, that the left-hand side R, and on the right-hand side S. I will denote this family of subsets in this way, funny way, that so this is clear, and this means something. And the question is, find the largest intersecting subfamily of this. And So let me show you a construction first. Fix one point here. Take all such sets which contain the R element set contains this point on the left-hand side, and on the right-hand side it has S elements in any way. So then obviously this will have this many on the right-hand side, and to every one we can choose any of them. So this will be the size of the family. And the second construction, surprisingly, if we fix the point on the right-hand side, and then we get this one. And the theorem of Frankl from 1996 is that one of them is the largest one, so which is the larger out of the two. This is absolutely the largest one. And his proof is algebraic using eigenvalues and tensor products. And so this is very important, that you can, because the sizes are independently chosen from the two sides, so you can take the product there. Let me mention some two-part intersecting results, just to show that there are much work in this area. So first of all, Attila Szali considered the following: in more general setting, the intersection was at least T, but there was an assumption that the intersection, sorry. No, that's, they are not empty. And the motivation was something, I am not sure that that's correct in this, the condition. So I think only you have to cross out G. So the motivation was that these were rectangular arrays, intersecting rectangular arrays, and if one of the sides is empty, then it's not a rectangular array. So because the empty set times something is just the empty set. But anyway, I don't want to state here theorems, just indicate that there were similar related results. And then many authors considered the following problem, that you exclude such a pair, this is a green set and the red set, only if they are equal in one side and disjoint on the other side. Of course, symmetrically we exclude also, and so this is forbidden. And then they determine the largest number of sets, and it will be more than the trivial 2 to the n minus first power when we just exclude disjoint pairs. And they also considered combinations of the Sperner property and intersecting property on one side, and so on, so many variations. And two Chinese mathematicians considered this problem when you take K element sets on the left-hand side and L elements in the total set. And again, the largest intersecting family, they determined it. Okay, so let me return to the main line. I call it a substar or trivial. Andrei Kupovsky called trivial construction when we fix one point and take all sets containing this fixed point. And I just repeat now Frank's theorem in this terminology, that instead of giving the formula, I say that the best is a substar or a trivial intersecting family. And but going back to the formulas, so can we tell which is larger? And if you compare these two sides, it's easy calculation that this is bigger than this one if this holds. So now my question is, when you have two kinds of sets, so R here, S here, or T here, U here. And of course, so it means that you choose from this union, the sets from this union. And so recall one page before, so the best thing to choose the point on the left-hand side if this is true. But if for both kinds of sets this inequality holds, then we know that the best thing is to choose the point on the left-hand side. But what happens if one is satisfies this one, the other one satisfies this one? Because Frank's theorem, according to Frank's theorem, for this one you have to take the point on the left-hand side, and for these ones, the right-hand side. And the result is that one of them wins. So there is no in-between situation. And so formally, this is the statement that if you choose the sets from this family, then the best solution is again a substar or a trivial intersecting family. But of course, this can be asked more generally, that we have sets of this form, R1 here, S1 here, R2, S2, R3, S3. So in full generality, you take this one where you fix these pairs RE, SE. And even under this condition, the best is to choose one point, so a substar or a trivial intersecting family. And I will sketch the proof. This is why I showed the cyclic permutation method, because the proof uses this method. So what do we get instead of the cyclic permutation here? We have two cyclic permutations in the two sides. So, and then we have to consider the direct product of these two cyclic permutations. So formally, I will denote it with this. So it's a torus actually, right? And what do we have instead of the interval? The interval, we have intervals in both sides. The direct product is a rectangle of this size. And of course, we have for different eyes, we have different rectangles, different shapes of rectangles. And so what is the condition for these rectangles? Then that they have to meet at least in one direction. I call them proj intersecting. I will show what I mean. So this is a rectangle. Of course, you can imagine that these are circular here and also in this way, but it would be very difficult to make a picture. So this is and this is another rectangle. And these are good because they are intersecting in this direction. So in this projection is intersecting, but not this, but one is enough. This is also good. But so this is what we forbid, that there is no intersection in neither direction. And so what we consider now, let Ri be the family of rectangles of this shape, and they are intersecting, so it's only one shape now. And we want to, the Ri is one shape, but we must have all of them intersecting, so all kinds of, all types. And so we can prove, so this is the hard part. We can prove that the best thing, if n1 and n2 are large enough, and the best thing is, I better show the picture, if there is a line and all rectangles meet this line. All possible rectangles we choose meeting this line, and then they will be trivially intersecting, or horizontally, vertically. So there is a line in the other direction, horizontal, that all rectangles meeting this line. And so in other words, it means that the total number of rectangles cannot be more than, so n1 is, sorry, wrong direction. N1 is the, that's the other picture, I guess. So N1 is this number. So every rectangle can start every point. So N1 times for every rectangle. And then this, we multiply it with the other size of the S1, because we can move them in this direction, because the size is Si, and we can move Si times to achieve that they meet this line. And so this is true for everything, every I. So this is for the case, this is the number of rectangles meeting a horizontal line, and for a vertical line, this one. And so this is what we can prove, but this is not enough to prove the theorem. This is the small disappointment. And so what we need is actually a weighted version. So the different rectangles have a non-negative weight. And this is also true for every linear combination. And this is already sufficient to finish the double counting, which is, yeah, I have time. So these are the families in the original families of this size, R, E, S, I, and we use this generalization of the double counting, so with a weight actually. So for all pairs of, so this is a pair of cyclic permutations and an F, and oh, sorry, this is this should be, yeah. So F forms a rectangle because the elements in both sides form an interval. So we take a pair of cyclic permutations and an F which is a rectangle in this one. And so this will be the weight what we will use, and then that's we substituting in the lemma we really get that again. So we really get the statement. So this is the end of the sketch of the proof. So I return to this name, trivially intersecting, and I want to I will use for some goal Hilton-Milner's theorem, which was told by several speakers here. So if it's not a trivially intersecting family, you cannot have more than this number, where the construction is that you fix one point and take all and you fix not only one point, but you take a k-element subset not containing this point, and you take all the sets, k-element sets, containing this point and meeting this k-element set, then it will be intersecting, and it's easy to see that the number is this. And so I suggested an open problem. So if F is a non-trivial intersecting subfamily of this, so now I return to Frankel's case, when we have only one kind of sets, so R elements here, S elements here, but it should, Frank's theorem answered the largest family, but it was the construction was a trivially intersecting family. So if we forbid triviality, then my suggestion was that take a Hilton-Milner here and combine the sets with all S element sets here. So then you get this number from Hilton-Milner and multiply with this. Or the other side, then you take, you get this one. So this was the conjecture, but it turned out that this is wrong. Because if you don't, so you fix this point, and you, instead of fixing a set here, and then you can fix a pair, which is avoiding this, and take all the sets containing this and meeting this pair. And in most cases, this is bigger than my conjecture. And Kwan, Sudakov, and Vieira determined the largest one, and this is this construction what they gave. I'm sorry, I forgot to correct this, because when I wrote this first, it was in March, so now it's a few months ago, but it's still quite new. And also for the multi-part case, they proved this statement. And so concerning my theorem, what I proved here, I showed the sketch. it should be true for more parts also. But the lemma becomes very complicated. Somehow I cannot finish. Hopefully someone will finish it. Because, you know, in 2-dimension one can see things, but in N or R or whatever dimension is harder to follow what is happening. So let me return to this important goal of the conference. So I am really impressed how much Stanley Fiorini is respected in this country. So even the church was decorated for this occasion, for his 75th birthday. So the chairman didn't expect me to finish so fast. I didn't either. Somehow, I knew that I don't have long time, so I tried to be fast.
Any questions? We have plenty of time, actually. Yes,
So, returning to the Erdos-Ko-Rado theorem, so your setting there is you have an n set and all the k subsets of S, and you're looking at the intersecting property. You can actually think of that as the k uniform matroid on a set of n elements. So is there any extensions of this to matroids? In particular, if you take a graph and you look at a graphic matroid and you look at all the spanning trees and ask what's the largest number of spanning trees you can have the complete graph such that every two intersect, and various other generalizations of that sort.
Yeah, so this kind of question was raised by Vera Schorsch and I don't remember, Shimonovich. So take a complete graph and find the maximum number of subgraphs such that the intersection contains a triangle. Of course, and this has been solved recently by Friedgut and co-authors. Anybody remembers? Yeah. But this is the non-uniform case. So the uniform case.
And all I would want
more,
is
more
intersection
difficult.
of at least one edge, just like in the Erdos-Ko-Rado setting.
Yeah, but I don't think it makes any difference. Fix an edge.
Fix it.
And it's a consequence.
And is that always the maximum?
Okay, we have to discuss it later. So my impression is that it's a trivial consequence of Erdos-Ko-Rado. But so you need some more. Okay. Andre, something.
Thank you. So just a question: the theorem that you presented with the with two sizes, two sizes, two different types of sets. Do you expect it to hold for any n, like, or this condition n being sufficiently large is necessary?
Yeah. So for the Erdos-Ko-Rado, there is a trivial bound when if it's less than, so n is less than 2k, then it does not hold, and here there is no natural bound.
Mhm.
That's the problem. So it must be anyway large enough. The question, of course, how large?
Yeah, but
And in my case, it's something like 9 times square of the largest out of all the numbers. So it's not very big. So it's not. I don't use Semiradis regulatory lemma. So
yeah, this I understand. But do you expect it to hold for linear n, like
yeah,
9,
yeah,
9,
probably
and
linear
9, a
is
maximum
enough.
of n1,
Yeah,
n2 or something?
yeah, yes, yes,
Okay,
yes.
thank you.